Good morning. This is going to be the first lesson in a series of 4 lessons where we talk about operations with radicals. Now, there's lots of different operators in math, but when people talk about like operating on functions or operating on radicals, usually what we mean is add, subtract, multiply, and divide. Those are the 4 main operations. Now we're going to start with the easiest of those 4 operations, which is multiplying. Kind of like with fractions, the easiest thing to do with fractions is to multiply them. And then as you try to add fractions, you actually need the common denominator, and radicals really work the same way. The easiest thing for us to do with them is to multiply them. If we want to add them, kind of like a common denominator, we need something called a common radicand. So I'm going to introduce a little bit of vocabulary at the get-go. A few classes ago, we introduced this number right there that would go in the hook of the radical, and that was called the index. Now, the number under the radical is called the radicand. And we'll refer to that more when we get to adding and subtracting. But just in case I throw that vocab word out, the radicand is the number underneath, or expression underneath the radical. Now, here's the principle. And I actually recorded this lesson. I got 8 minutes into the lesson and realized I left out a really important word, and there was no way to rewind the video and fix that I had left out a word. And so I had to start it over again. So I understand the frustration when you have to start things over again. Oh, here we go. Let's see if I can do it right this time. So we have the square root of a times the square root of b. Now, these are going to work for all kinds of radicals, like third roots, like cube roots, fourth roots, fifth roots, and so forth. But because square roots are the most common kind of radical that you would ever see, we're going to focus our study on the square roots. And then if you are in a class in the future where these operations are taken up a notch, you'll have the groundwork in place because the principles are going to be the same. Remember that math is consistent. So if you are multiplying 2 radicals, the radicands do not have to match. Okay, you can have 2 totally different numbers here. And what you would do is you would just multiply the 2 numbers together and write them under a radical. Now, there's one provision here. When you're reading a math book, not that math books are really popular for reading, but if you've ever looked in a math book, you know that there are like the boxes and the highlighted sections, and you know that that's something important. That's the formula. That's the theorem. That's the thing that needs your attention, and nobody reads anything else that goes along with it. This would be the big highlighted box, and then there's always the little blurb next to it that explains the theorem or the formula or whatever, and people tend to ignore that, but we don't want to ignore it here. This property only works if A and B are not both negative. And the word that I left out earlier was the word not. And I said it in the verbal part, but I didn't write it, which is confusing for students if the teacher says one thing and writes something else, especially in a video where you cannot raise your hand and ask me, what are you talking about? So I felt I needed to go back and fix it. So this only works if A and B are not both negative. And I will show you an example in a little bit of what happens when they are both negative. But before we do that, let's look at 3 examples of multiplying radicals. We're going to start with the easiest, and then we'll work our way up to some more complicated ones. There's actually nothing like really intense in this lesson. This is probably going to be a pretty short lesson. So example 1 is the square root of 2 times the square root of 5. And again, the radicands don't have to match. You can multiply them. You can't add them. So when we get to the adding, we have an issue. But multiplying, we're totally okay. I usually skip this step, okay? But I'll do it out just this once, just to make sure that everybody's clear with what we're going to do. We are able to multiply the 2 radicals together, and we get the radical of 10, or square root of 10, or root 10. Typically, I would skip from here to here, okay? And I will do that in the future. I am not going to write out the multiplication, nor do I expect you to do it. Example 2. We'll do the square root of 2 times the square root of 6. So at first you're like, this is going to be really easy. That's just going to be the square root of 2 times 6, and 2 times 6 is 12. Ta-da! Like easy peasy. Now, this is where it gets a little bit complicated. You can actually simplify the square root of 12, and it will be expected that you will simplify any of your answers. So after you multiply, you cannot just walk away from the problem. You have to ask yourself, can I simplify that? And 12 can simplify. Here's why. Because this is a square root, so you would be looking for something squared. Okay, kind of going back to our lesson on simplification. You have a factor of 2 right here, and there's also a factor of 2 in the 6, because 6 is 2 times 3. So you end up with 2 times 2 times 3, and 2 times 2 is 4, which means that you have something that can come out of the square root. You can simplify that either way that we've gone over. The original way we went over it was for you to take the 12 and factor it with the perfect square. So it's almost like we're going backwards in the problem, just with different factors. So we started with the 2 and the 6, and now we're breaking up the 12 a different way into the 4 and the 3. That is exactly what we're doing. The square root of 4 is 2, and so our final answer would be 2 root 3. If you've struggled with that, with the finding the perfect square factor, you can also do what we did in the last lesson on simplifying the radicals, where you would do the prime factorization of 12, which is 2 times 2 times 3, and you might do a little scratch work for that. You say, oh, well, that's 2 times 6, and 6 is 2 times 3, and so you get the 2 times 2 times 3. Now, remember, if it's a square root, you are looking for a group of 2. And there it is. Ties into what I was saying a few minutes ago about the 2 and the 6, and you have the 2 factors of 2 coming in. Well, the square root of 2 squared is just 2 that comes out of the radical, and you're left with root 3. I don't care how you simplify it, as long as the process makes sense to you. I don't want you just replicating what I do in this series of steps. The steps should make sense. They should be logical. You should understand why you're manipulating the problem the way you are and what your end game is. Like, what are you trying to get at the end? You're trying to get the smallest number under the square root possible. Third example. This one, in some ways, I feel like this one should be obvious, but it's not. It actually does tend to trip people up. And there's a couple ways that you can think about this one as well. So for this one, we're going to do the square root of 3 times the square root of 3. And I'm actually going to work the problem again over here on the right-hand side. And so we can kind of reason through it 2 different ways. If we do what we've been doing in this lesson, then we would look at this and we'd say, okay, the square root of 3 times the square root of 3, we do 3 times 3 is 9, and the square root of 9 is 3. Okay, and you can work it out that way. Or you can think about it a different way. It's just kind of a different way of getting your head around what's happening in this problem. When you multiply something by itself, that's called squaring. So we have the square root of 3 times the square root of 3. Well, another way of writing that would be the square root of 3 squared. But remember from our lesson on radicals that these are what are called inverse operations. Square rooting and squaring undo each other, kind of like adding and subtracting. So you have a 3, you do something to the 3, and then you undo it. Well, if you do something and then you undo it, you will be left with whatever you started with, which is 3. So those are just 2 different ways to think about it. Obviously, they come to the same answer, the same solution. The answer is 3. It's just 2 different ways to get there. Do whatever makes the most sense to you. Do whatever is going to be quickest and easiest for you that you feel confident that you can explain to somebody else, this is what I'm doing, this is why it works. Now, let's address this idea here, that it only works in A if A and B are not both negative. So that raises the question, what happens if A and B are both negative? Why doesn't it work? Can we kind of get our head around why it doesn't work? So we're going to do this with just what's called like a counter example. I'm going to give one example of 2 negatives. We're going to show that it doesn't work, and that is enough to exclude it for the 2 negatives forever, because it's a counter example here. So we're going to do the square root of 4 times the square root of 4, or negative 4, sorry. Square root of negative 4 times square root of negative 4. And we're going to show that that is actually not equal to the square root of negative 4 times negative 4. So that kind of harkens back to this. where you have the two radicals multiplied together, and then you just take the radical of the product, and we're putting that little not equal. Okay, so if A and B are both negative, this actually does not hold, and it's not going to be equal. So let's do this out. If I take the square root of -4, okay, quick little refresher on the square root of -4. The square root of -4 is equal to the square root of 4 times -1, which is the square root of 4 times the square root of -1, which is 2i. Okay, kind of put that out there, and then we'll make it go away. Square root of -4 is 2i times another square root of -4. I don't know, I'm having issues with my time sign there, which is 2i. Over here, I have square root of -4 times -4. Well, a negative times a negative gives me a positive. On the left-hand side here, 2i times 2i, well, 2 times 2 is 4, and I times I is I squared. Over here on the right-hand side, the square root of 16 is 4. Remember from our study of complex numbers, I squared is equal to -1. So we have 4 times -1. And I'm actually done with the right-hand side, so the 4 just kind of comes down. And then on the left, 4 times -1 is -4. And indeed, -4 does not equal 4. Those are actually two totally different numbers. And so if A and B are both negative, you end up with this happening. And you could like prove this, I guess, by like taking out the specific number example and just putting in a variable. And I don't really want to think about it. But what's going to happen on the left is you're always going to get something with an I, and the I is always going to end up squared, and it's going to make your answer negative. What's always going to happen on the right is the two negatives are going to multiply together to give you a positive, and the negative goes away. So it's always going to come back on the left. It's never going to come back on the right, and it's never going to be equal. So if A and B are both negative, this property actually doesn't work. Okay, I actually just have one more thing to do, and it's taking a look at multiplying. The name for this is actually kind of scary sounding. Multiplying binomial radical expressions. You know what? Let's actually put that up there. Let's not be afraid of the language. Binomial radical expressions. So it sounds like a mouthful, but we actually know what they are, and they're not anything we need to be afraid of, and it's good to pull apart this vocabulary and get on the same page with it. We know actually from the last test. So one of the questions on your last test was identify this as a monomial, binomial, or trinomial. So we know as soon as we hear the word binomial that we're talking about two terms. Okay, so pretty much that means you got something added or something subtracted. You got like two things, and they either have a plus sign or a minus sign between them. Radical just refers to this, and I'll put the little n in there. That was like a really terrible n. Let's see if I can do a better n. Oh, there we go. That's a radical. So we're talking about two terms, some kind of radical, and then an expression is just something with no equal sign. Okay, it's some kind of hodgepodge of numbers and letters with no equal sign. Because if it had an equal sign, it would be an equation and we would solve it. So binomial radical expression is two terms with some kind of radical in it, and there's no equal sign. I'll give you an example so that we are all together. 2 plus root 3. That is a binomial because it's got two terms. It's a radical because it's got the radical in it somewhere, and there's no equal sign. It's just 2 plus root 3. There it is. It's great. So what we're going to do in this next part is we're going to multiply binomial radical expressions. It's really not that bad. So this is the example, 2 plus root 3, which is why I wrote it down because it was staring right at me, plus 4 root 5. Okay, this is actually going to be doable in one step. I might do another example just for fun. Yeah, I'll do another example just for fun. So here we go. These are two binomials, so we do need to FOIL it together, okay, or distribute. I prefer to think of it as distributing. And FOIL comes in handy as a verb. We do 2 times 4, which is 8. Remember, that little orange line has nothing to do with the problem. You do not have to put the little orange lines in. I just put the little orange lines in because it helps you, the student, to kind of track with your eyes what I am doing out on the page. It's the only reason the orange lines are there. Then we have 2 times radical 5. Well, that's just 2 radical 5. Like, don't overthink that. That's just 2 radical 5. 2 times radical 5. That's all it is. Now, in the inner part, that I'm going to do a little bit of scratch work over here. That is root 3 times 4. But remember, like the rule we had where anything that's not under the radical, we're going to kick around front, because we want it really clear that the 3 is under the radical and the 4 isn't. We don't want something like this where we're just not sure if the 4, like, is the 4 supposed to be under the radical? The time sign looks like it's under the radical, but what about the 4? The 4 can't make up its mind, and we don't know. So we rewrite it in a way that there's not going to be any ambiguity at all. So we're going to write it as 4 root 3. And then root 3 times root 5 is just going to be the square root of 3 times 5, which is 15. And that's literally all you can do with this problem at this point. There are binomial radical expressions where you might need to do more, but that's literally all there is to it. Let's do one more. I'm actually going to pull this off of the classwork practice. So I'm going to work it with you guys instead of having you guys do this one on your own, because it becomes important in the next lesson. So here we have 2 binomial radical expressions, and I hope you're looking at them and saying, oh, we've seen those. We've seen those a lot. Those are so special. We actually love seeing them. We're excited. Those are conjugates. And we know when we multiply conjugates, we can expect wonderful things to happen. So let's go ahead and multiply them. 2 times 2 is 4. 2 times negative root 5. Okay, I'll just do my little scratch work. Positive times a negative is a negative, so it's going to be negative 2 root 5. This in the middle, root 5 times 2. Remember what we just did. We're going to take that 2. We're going to move it to the other side because we don't want that confusion. And then minus the square root of 5 times the square root of 5, which is the square root of 25. What happens with conjugates, it's why we love them so much, is the middle terms cancel out because math is consistent, and this is what conjugates do. So minus root 5 plus root 5, 2 root 5, but you know what I'm looking at. Minus 2 root 5 plus 2 root 5. There we go. And then the square root of 25 is 5, and we end up with 4 minus 5, which is negative 1. And I would like you to note, there is no square root anymore. Just like when we multiplied complex conjugates, we didn't have any I anymore. Okay, so that was actually one of the 6 practice problems. So I'm going to put the other 5 up on the screen there. And at the time of this recording, which is about a week before we actually do the lesson, I have no idea how I'm going to structure the classwork. You will find out because I will tell you in class what we're going to do. But here are the practice problems. Okay, so here they are. We have the square root of 3 times the square root of 5. You're like, this is so easy. I got this. Then the square root of 3 times the square root of 6. That's going to be like the second example that I did. So you can go back in your notes and look at the second example. Then we have the square root of 4 times the square root of 4. That's going to look like the third example. Then we have the multiplication of 2 binomial radical expressions. And so you can look at the third and fourth examples. Then we get to the 5th one, which is where it gets fun. I did not give you any examples that had variables in it. But you know enough by now that you know that math is consistent. So whatever worked with the numbers is also going to work with the variables. And it just so happens that you know how to simplify radical expressions that have variables in them because we spent the last 2 class periods working on it. So 5 is where it really starts to stretch what you know, where you're not just mimicking what I do, but applying that knowledge to try to move a little bit further. So I'm excited to see what you guys can do with it, and we will do whatever we're doing for the classwork problems next.